Hello, class. This is going to cover the repeated measures analysis of variance. And to make it easy for you to contrast repeated measures analysis of variance with the between subjects analysis of variance that we already covered, I basically used that PowerPoint as my starting point, and then I tweaked some of the formulas and things like that as needed, but it should make it easy for you to compare and contrast between those two different types of tests. So the repeated measures analysis of variance or within subjects analysis of variance compares the means across two or more time points or two or more conditions within the same person. So we're going to show an example where we have salary, and we're going to have salary for each person at three different time points. And then we're looking to see the change of salary across time. So it's inherently a within subjects design, and you can actually combine between subjects and within subjects together. We don't get into it too much in this class, but that's called a mixed ANOVA. So if we wanted to look at gender differences between men and women in salary across time to see if the disparity between men and women gets bigger across time or if it reduces with time and experience and negotiation, we could use a mixed ANOVA to look at men versus women across multiple time points, and we would need each man and each woman across those time points to do that. In this case, though, we're going to focus on the within subjects of the repeated measures, and we're going to do what's called a one-way repeated measures or one-way within subjects ANOVA, because we're only going to want to look at one factor, and that factor is time or condition. In this case, we're going to look at salary during college, which was about 25,000 on average, right after college, so the first job after college, which is 49,000 on average, and then 10 years post graduation, which is about $78,000 on average. And in case you're wondering, these numbers, there's a lot of variability depending on what you decide to do post graduation. However, I did pull them from the Bureau of Labor Statistics just as a rough estimate. So I'm combining a lot of things together in order to get these estimates, which is why I don't cite anything in particular, but they are roughly close to what you might would expect. In this case, we still refer to K. Before, in the between subject, K was our number of groups. So if we were comparing three different groups of individuals, then we would have had K equals 3. In this case, it's the number of time points or the number of conditions. So in this case, because we look at salary during college, right after college, and 10 years after college, then we have K equals 3, because that's the number of time points. We also have the number of participants, and I'm going to show you an example where we have 5 participants, but of course it would depend on the number of actual participants, and we use little n for that. Our F obtain is very similar to what we saw before. So now instead of between group differences, we're going to refer to this as between time differences, but it's relatively analogous to what we did before. And that's going to be represented by mean squares time. Unfortunately, that mean squares time is actually called a lot of things. So in our case, because we're looking across 3 different times, and time is largely the variable that we're interested in, that is probably the most appropriate term, but sometimes you'll see this as mean squares effect, mean squares between, mean squares condition, mean squares treatment, and depending on the literature that you're reading, you may see all of those. So do be aware that there are a number of alternative names that are used for that. We're going to divide that by the error or the unexplained variability. And this is different from the error term that we used before in a little bit, because now we're partialing out the error or the variability that is due to the subject. So ultimately, if we look at within subjects versus between subjects ANOVA, the within subjects ANOVA should have more power. The same way that when we looked at dependent samples t-test and independent samples t-test, the dependent samples t-test had more power because we are accounting for the individual variability. We're partialing it out. It no longer goes into that error term. Because of that, the denominator is ultimately going to be a smaller number. We're then going to compare the F obtained to the F critical. The exact distribution, of course, will depend on the number of degrees of freedom, but this gives you one example of that. And for those degrees of freedom, we still have degrees of freedom between or time or condition. Again, there's a number of terms similar to mean squares, time, condition, effect. All those would still apply. It's going to be similar to what we saw before though, where K minus 1, so the number of time points, number of groups, minus 1. The error term is going to be the number of individuals minus 1 times the number of groups or number of conditions, number of time points minus 1. And then the total degrees of freedom would be equal to the number of people times the number of groups minus 1. So in the example I'm going to show you, we're going to have 15 individuals across 3 time points. So between, degrees of freedom between would be 3 minus 1, 2. The degrees of freedom error would be 5 minus 1, which would give us 4 times 3 minus 1. So we're going to have 4 times 2, so 8 degrees of freedom for error. And then the degrees of freedom total would be 14. So 3 times 5 minus 1, which would be 15 minus 1, gives us 14. When we go to calculate this, the mean squares time is going to be the sum of squares time divided by degrees of freedom time. Very similar to before, it was mean squares between is the sum of squares between divided by degrees of freedom between. To calculate the mean squares time, what we're going to do, we could do this for each individual, but instead we're going to look at the average for each time. So the average for the first time, time 1, in college, the average salary is $25,000 while you're working on your degree. And we're going to see what is the difference, the deviation of that from the grand mean. The grand mean would be equal to the average of all of the people across all the times. So if we take 23,000 plus 46,000 plus 72,000 plus 24,000 plus 47,000 plus 75 plus 25 plus 49 plus 78 plus 26 plus 51, if we take the averages for all people across all 3 time points, their average is $50,667. And we see that bolded in the bottom right corner. Now, for sum of squares time, we want to know what is the deviation of 25,000 from that, but then we need to account for the number of people that are in that estimate. So we're going to multiply by n. Then we're going to look at the deviation for time 2, 49,000 from 50,667. Again, multiply it by 5. And then we're going to look at time 3, 78,000 minus 50,667. Multiply that by 5. And of course, we need to square all of these estimates to deal with the fact that 25 is going to be below the average, but 78 is going to be above the average. And really, we care about total variability, total deviations. And so we have to square it to deal with the fact that some are going to be positive, some are going to be negative, similar to what we saw before. With mean squares error, this is going to be the sum of squares error divided by the degrees of freedom error. The way that this is different than what we saw for our denominator when we did the between subjects ANOVA is that we now also subtract out variability that is due to the subject. So we're going to take the sum of squares that is related to the subject, attributable to the subject. We're going to subtract that out from our error term, and thus the denominator should be smaller. And because of that, our F obtained would ultimately be bigger if all things were equal between those two designs and we compared it between subjects and within subject. So some of the things that you see in this formula for the sum of squares error, sum of squares total, and sum of squares subject. So sum of squares total is exactly what we saw whenever we did between subjects. It's each individual score. So all 15 scores, so the 3 time points, 5 people, we have 15 scores. We're going to subtract the grand mean of 50,667 from all 15 of those. So we can see that here. So we're going to take the square deviation of 23,000 from 50,667, add to it the square deviation for 46,000 from 50,667, and 72,000 to 50,667, 24,000. So we're going to do that across all 15 of those scores. Add those together, that'll give us sum of squares total. So that's the total variability within our data. We're then going to subtract time, so the sum of squares time that we got in the previous slide, and we're going to subtract the variability that's due to the subject. So to get the variability that's due to the subject, what we're going to look at is each individual's average. So Bill on average, if you look at 23,000 plus 46,000 plus 72, Divide that by 3, so you get the average for Bill. His average salary is 47,000. Now, that may not be his average across his entire career, but across these 3 time points that we're interested in, that is his average. How much does that deviate from 50,667, our grand mean? Square that, and then we're going to multiply it by k, multiply it by our number of groups. And we're going to do that for each person, add those all together. And that gives us sum of squares subject. So now what we're doing is partialing out the variability. So Bill not doing quite as well as Jess, for instance, right? She seems to be rocking it. Congrats to her. Bill's not doing quite as well. Maybe he doesn't need to. Maybe he's relatively well off financially. He has a spouse or a partner that makes good money, or he has a trust fund. I don't know what's going on in Bill's life, but maybe he has a job that he absolutely loves, just doesn't make quite as much money doing it. And with that, he is doing a little bit more poorly than Jess if we're just looking at numbers. And because of that, he is then going to be different from the overall average of 50,667.